So yeah, guys, welcome to this is the fourth of our seminar series, and I'm really happy to have Mark Lowe today because he's definitely one of the best researchers that I've met while I was doing my PhD in London, and he's working on inductive logic programming, which is a very relevant topic nowadays, because especially for us, because it connects machine learning with logic. So I think it's super useful, and people don't really talk enough about it, I would say. So I guess he's gonna talk about the frameworks that he's been producing over the years, some of which I'm using myself for research purposes. And yeah, so Mark, you can start whenever you like.
Okay, thanks, and thank you for the introduction. That was very kind. So as Fabio said, I work on inductive logic programming, specifically on learning answer set programs. Today, I'm going to focus more on what the systems that I've built can do and the underlying theoretical learning frameworks, rather than how the systems themselves actually work. But if people have got questions on how the systems work, I'm happy to take those as well. And I was saying before everybody joined, I'm quite happy to take questions throughout rather than answering the questions at the end, because I think it's better if everybody follows the whole way through. Okay, so as humans, we are all capable of performing very high-level cognitive activities. So we can learn from our past experiences, we can make predictions using the knowledge that we've learned, and if we already have an existing knowledge base and we encounter some new information that isn't covered by this knowledge base, we can revise or extend the knowledge that we've previously learned. And crucially, we are able to communicate what we've learned to other people. So in order for machine learning solutions to achieve real human-like performance and real human-like levels of cognition, it's vital that they're able to do all of the four above things. And some of the forms of machine learning that you may have seen in the past, if you're inductive logic programming, are very good at some of these things, like learning from past experience, but they fall down when it comes to communicating the knowledge that has been learned. What I work on is called inductive logic programming. So the goal is that we're trying to learn a set of logical rules called a hypothesis, such that when it's combined with an existing background knowledge base, it explains a set of examples that we've been given. So the key advantages to ILP compared to other forms of machine learning, firstly, the hypotheses are all human readable because they're expressed in logic. And so this means that we could easily translate them back into English or Italian, I suppose. And we can define useful concepts in the background knowledge. So this means that if we already know some of the concepts that support the concept we're trying to learn, we can encode them in the background knowledge, and then rather than having to start from scratch, we only learn the pieces of information that we're missing. If you have come across ILP in the past, it's likely that you've seen systems that target learning prologue programs. So as I'm sure most of you are aware, there are different forms of logic programming. In particular, in this talk, I'm going to focus on answer set programming. So if you haven't come across it in the past, it's a very expressive declarative formalism for logical reasoning. And when we're writing answer set programs, usually the idea is that we start with a real world problem that we're trying to solve. We encode it as a set of logical rules called an answer set program. We then use an answer set solver to find what are called the answer sets of the program. And these are essentially just a special subset of the models of the program, such that each of these answer sets then corresponds to one of the real world solutions of the problem that we're trying to solve. So it's got some really nice features for representing complex knowledge. Similarly to Prolog, it has negationist failure, which means that we can very naturally model things like defaults and exceptions. So we can do common sense reasoning. And then in addition to what's supported Prolog, we also have choice rules and weak constraints. So choice rules allow us to model things like non-determinism and user choice, and will generate multiple answer sets. So if we have a choice of things that we could put in our answer set, then we'll usually get several different answer sets where we've chosen each of the different options. And then because general answer set programs have multiple answer sets, just like real world problems tend to have multiple solutions, we can easily model preferences over these answer sets using weak constraints. And so when we do this, we get an ordering of how good the answer sets are effectively. So for example, we could have an ASP program that encodes all of the paths to get from one place to another, and then we could put some preferences as weak constraints. For instance, we could say we're looking for the shortest path and use an off-the-shelf ASP solver to find the optimal answer set in terms of those preferences, or an optimal answer set. There isn't always a unique one. So before I started my PhD back in 2013, as I said before, most of the approaches to ILP focused on learning Prolog programs, but there were some existing approaches. But largely these could be categorized as either brave or cautious. So the brave approaches tried to cover all examples in at least one answer set of the program, and the cautious approaches tried to cover all examples in every answer set of the program. And what I showed very early on in this line of research was that there are some ASP programs, in fact, some very simple ASP programs that can't be learned with either brave or cautious induction on their own. And this is no matter how many examples you give the learning system, and even if you had a perfect learning system for brave or cautious induction, it wouldn't be able to learn such programs. And actually you need a combination of brave and cautious reasoning within a learning framework to be able to learn general ASP programs. And this leads me on to the learning frameworks that I developed in my PhD. So there are several of these. The most simple learning framework was called Learning from Answer Sets. And this is very different to previous approaches to ILP, because instead of the examples being atoms, they are actually examples of what should or should not be an answer set of the program. The reason for this change is that giving examples of atoms when you're learning Prolog programs is very natural, right? Because the output of a Prolog program is a query. You say, is a particular atom true? And the Prolog reasoner will answer either yes or no, right? In ASP, the main outputs are the answer sets. So it makes sense that when you're trying to learn an answer set program, you should give examples of what should or should not be an answer set of the program. In fact, our learning frameworks are slightly more general than this, in that we can give examples of what should or should not be a partial answer set of the program. So more formally, what I mean by a partial answer set is in fact what we call a partial interpretation. This is a pair of sets of atoms called the inclusions and the exclusions. And we say that an answer set extends a partial interpretation if it includes all of the inclusions and doesn't include any of the exclusions. Sorry, was that just a cough, or does somebody have a question? I think someone has left their mic.
Just a cough.
Yeah, okay. So those are the form that our examples take. A learning task for us then consists of a background knowledge. So just as in ordinary ILP, the background knowledge just includes all of the rules that we already know, so concepts that we already know, and a hypothesis space. That's the second element of that tuple, SM, where the hypothesis space is just a set of rules that are encoded in ASP. So for this learning framework, it's normal rules, choice rules, and hard constraints. I'll get on to learning weak constraints later. And then two sets of examples called the positive and the negative examples. Each of these examples is a partial interpretation, as I described on the top of the slide. For the positive examples, it has to be the case that there is at least one answer set of the background knowledge combined with the hypothesis, such that that answer set extends the partial interpretation. So that means there has to be at least one answer set that contains all of the inclusions and none of the exclusions. Now, this doesn't have to be the same answer set for every positive example. So it is possible to express there should be something that's true in one answer set and false in another. And then our negative examples say the opposite. So they say there should be no answer set that extends a given partial interpretation. Now, going back to what I was saying before, I said that in general, we need a combination of both brave and cautious reasoning in order to learn general ASP programs. It's our positive examples that enable the brave reasoning, because they say what should be true in at least one answer set of the learned program. And our negative examples enable the cautious reasoning, because by saying what should be true in no answer set of the program, you can equivalently represent what should be true in all answer sets of the program. Any questions on this before I move on? No? So I'll give an example, actually. So this is an example of a learning problem that we could represent within learning from answer sets. And the goal here is to learn the definition of what it means for a graph to be Hamiltonian. So a graph is Hamiltonian if there is at least one cycle in the graph that touches every node exactly once. In order to learn this, we give examples of both Hamiltonian and non-Hamiltonian graphs, where the positive examples are those that are Hamiltonian and the negative examples are those that are not Hamiltonian. The examples, I'm not sure if you can see my cursor, but on the top right-hand side of the slide, you can see a partial interpretation which represents the graph on the top left-hand side of the slide. So we've got, in the inclusion set, we've got the size of the graph, and we've got all of the edges which are in the graph. And then on the right-hand side, in the exclusion set, we've got all of the edges which are not in the graph. Now, this is a complete representation of a graph, just to keep things simple. If we wanted to make it more complicated, we could have partial graphs where we have edges that don't occur in either set. But I'm going to miss out that detail now, just to keep things simple. And then on the bottom left-hand of the slide, you've got a background knowledge, which basically just defines what it means to be a graph. Now, if you're not familiar with the syntax of ASP, don't worry, I don't want you to focus too much on that. But roughly speaking, what it says is that a graph can be exactly one size between 1 and 4. So it's either size 1, 2, 3, or 4. And if we have a graph of size n, then the nodes are labeled 1 to n. And between every pair of nodes, there is either an edge or no edge. On the right-hand side, bottom right, we've got the hypothesis that we're trying to learn. And in fact, if you give a sufficient number of examples to our learning system ILASP, it is able to learn this hypothesis. So again, I don't want you to worry too much about the syntax if you're unfamiliar with ASP, but what this says is that we pick a subset of the edges, which we're saying are in the Hamilton cycle, labeled with the predicate HC for Hamilton cycle. And then once we've guessed at this set of edges, we try to prove that this set of edges corresponds to a Hamilton cycle. So we have a recursive notion of what it means to be reachable from the first node in the graph by the second and third rule in the hypothesis. And then we've got two constraints. The first constraint just says that we want to rule out any answer set where we have a node in the graph that isn't reachable using the nodes in the Hamilton cycle. And the second constraint, the bottom rule in the hypothesis, says that we can't have two edges in our Hamilton cycle that start at the same node and finish at two different nodes. And this is actually equivalent to the correct definition of Hamiltonian. And as I said before, if you give sufficient examples to our learning system, we are able to learn this program.
Sorry, can I just ask, just curiosity? I see obviously the reason why the example uses a binary property. Is this necessary? Is it necessary that you have, binary property I'm referring to here is there being an edge, right, which is binary. You either have or you don't have an edge between two nodes. Is this meaningful also for properties which are not binary in this sense?
So could you give an example of what you mean by non-binary? Do you mean that?
Well, sometimes, well, if you take statistical hypothesis, rejecting or not accepting the hypothesis just don't mean the same thing. So failing to reject doesn't mean that you accept.
Okay, so yes, we can represent non-binary properties in that sense. The only thing that's binary is whether the example is covered or not, right? So the atoms themselves that are in the partial interpretation can represent things which are non-binary. So it could be that instead of having edge, we can have some other predicate that has a value where we have a fixed set and then an output value, if you see what I mean, and that can represent things that are non-binary. But the example itself will either be covered or not covered, because there will either be an answer set that contains all of the inclusions and none of the exclusions, or there won't be such an answer set.
Okay, thanks.
Yeah, okay. So that's the basic learning framework, the learning from answer sets framework that we introduced about 6 or 7 years ago now. Since then, it's been extended in quite a few different ways. So the first way that I want to talk about is with a notion of context-dependent examples. In standard ILP, and with the examples that I've shown you so far, we're searching for a fixed program that covers the example. So it's a fixed background knowledge and one hypothesis that covers every single example. In ASP, we don't usually use programs in this way. So normally we have a general set of rules, and then when we're trying to solve an instance of a problem, we'll quite often add a set of facts to those general rules and then solve the problem based on that problem instance, right? And then when we have a different problem instance, we'll add a different set of facts. So it was this that motivated giving a notion of context-dependent example. And this is now where each example can come with its own example-specific context. And now rather than this fixed program B union H having to cover every example, it's B union H union the example-specific context that covers a particular example. So this can be quite useful for representing things that are naturally context-dependent. For instance, say we had weather conditions, we could say in the context of rain, we want the program to behave in a certain way, and in the context of no rain, we want the program to behave in a completely different way. So we give different examples with different contexts. In addition to representing things which are naturally context dependent, we can also transform non-context dependent representations for reasons of efficiency. So this was the problem that I showed you before on Hamiltonian. We can actually encode this in a completely different way using context dependent examples. So rather than before where we had this partial interpretation that said which edges were in the graph, and we had a background knowledge which actually generates all of the different graphs. Instead, what we can do is just give a set of facts in the context that say exactly which edges are in this graph and exactly which nodes are in this graph. So now we don't need any background knowledge at all. And so it actually means that this context union the hypothesis, in the case of a positive example, has to be satisfiable, so have at least one answer set. And in the case of a negative example, it has to have no answer sets. The reason why we might want to do this for problems that can be represented in a non-context dependent way is that it can actually be extremely efficient. So with the previous representation, if we gave this to our learning system ILASP, it would have to reason about all of the answer sets of the background knowledge and then actually cut them back based on the inclusions and the exclusions. So there's this extra reasoning which is actually unnecessary. Whereas if we just give the context, then we only have to reason about the answer sets that are actually given. Also, more fundamentally, it allows us to represent problems in a slightly more natural way. So you'll notice when I give the background knowledge, I have to give an upper bound on the size. So if I have a new example that comes along now that is a graph of size 5, I have to alter the background knowledge in order for that example to work. Whereas when you've got context-dependent examples, you don't need to do that. You just carry on adding the examples and it will be taken into account. Now, it doesn't seem much of a change if I have to just increase the size by 1 in the background knowledge, but in more complicated examples, we might have to completely re-engineer the background knowledge in order to support further examples. Okay, so that was the first extension. The second extension I want to talk about is weak constraints. So I mentioned these before. They give a preference ordering to the answer sets of a program. So again, please don't worry about the syntax if you're not familiar with ASP. But roughly speaking, what this set of weak constraints does is creates a preference ordering over a set of possible journeys from one location to another. So a user is trying to get from one location to another, and they have these preferences, which say the first weak constraint says, I want to avoid walking through areas with a high crime rating. The second one says that we want to minimize the number of buses that we take. And the third one says that we want to minimize the total walking distance of the journey. These are ordered in terms of priority. I've seen a hand's gone up.
Yeah, you were actually going to say that, so sorry, I'll put it down.
Oh, okay, that's fine. So these are ordered in terms of priority, which means that the first preference is infinitely more important than the second, meaning that we try to resolve that first and we only consider the lower preferences if we have two journeys that are equal with the higher preferences. Okay. Now, if we give these preferences along with a set of journeys such as the ones on the slide to an ASP solver, then it is able to rank the journeys or find the best possible journey given a set of preferences. What we're interested in doing is learning these preferences from examples. Now, the examples I've shown you so far are incapable of learning weak constraints, and that's because they only say what should or should not be an answer set of the program. Weak constraints don't affect what is or is not an answer set of the program, and so you can't learn weak constraints with examples of this form. Instead, what we need to do is give examples of which answer sets are preferred to other answer sets. So an ordering example for us is just a pair of the examples that I showed you before, expressing that the first example is preferred to the second. That's slightly, roughly speaking, there's actually it's actually slightly more complicated than that, in that there are two different forms of ordering examples, because if you've got partial interpretations, you may express either that at least one of the first kind of example is preferred to at least one of the second kind of example, or you may want to say more cautiously, similar to the cautious reasoning before, all of the first sets of examples, or all of the answer sets extending the first set of example, are preferred to all of the answer sets extending the second example. But just roughly speaking for now, we can think of it in terms of one example is preferred to the second. Now, given sufficient examples of this form, we can learn the weak constraints that I showed you on the previous slide. So those are some of the extensions. There are other extensions that I'm not going to go into detail on in this talk, but I'm happy to answer questions about those extensions if people are interested. You may ask what these extensions give us in terms of the generality of the learning framework, or even given that we're using partial interpretation examples, and this seems like a much more complicated way of learning things compared to, say, brave or cautious induction, where the examples are simply just atoms, whether this actually gives us any advantage. And a couple of years ago, we had a paper in the AIJ that was investigating this in great detail. So what we were trying to investigate really was a generality ordering of the learning frameworks in terms of their theoretical upper bound in terms of what they can learn. So we're not worried about particular systems and how efficient they are, or how good they can learn from a particular data set. What we're trying to work out is if we had a perfect system for a learning approach and a perfect data set, is it even possible to learn some ASP programs? The way that we did this was we defined a new notion called distinguishability. We say that a framework can distinguish one hypothesis from another hypothesis with respect to some fixed background knowledge if we can produce a learning task in that framework with that background knowledge such that the first hypothesis is a solution and the second is not. Because if we can do that, it means that if we have a perfect system for that learning framework and we're given sufficient examples, so for instance, the ones in the learning task that we've produced, we are able to distinguish the first hypothesis from the second. And what we showed was that if you use this measure of distinguishability as a measure of the generality of a learning framework, learning from answer sets is strictly more general than both brave and cautious induction. And actually, in fact, there are some programs or pairs of programs that can't be distinguished with either brave or cautious induction, that can be distinguished with learning from answer sets. And that the extensions that I just showed you, so adding context and then adding ordering examples to learn weak constraints, strictly increase the generality of those learning frameworks. The final thing that we showed was that actually the most general learning settings, so the ones with context-dependent examples and ordering examples, is capable of distinguishing any pair of ASP programs so long as they are not strongly equivalent. And for those of you that aren't familiar with the term, effectively that means that there is some way of the programs behaving differently. I would argue that that's about as far as you'd want to go with the distinguishability of a learning framework, because you don't want to distinguish between two programs that behave exactly the same. And so this is actually quite a fundamental result for our learning approach. So on the other side, though, you might ask, with this increased generality, is there any cost to the increased generality in terms of computational complexity? So the results that are shown on this slide are all in terms of propositional versions of the learning framework. I am working on upgrading these to first order versions, or at least function-free first order, but we haven't published that yet. Just to go into a little bit more detail, there's 3 decision problems that we're considering here. The first verification is verifying that a hypothesis is a solution of a given task. The second is verifying or checking that a given learning task is satisfiable, so it has at least one inductive solution. And the final one is checking that a given hypothesis is an optimal solution to a given task. Brave induction, so that's the one where you're trying to cover all examples in at least one answer set of the program, has a lower computational complexity than any of the other learning frameworks. But interestingly, even though the learning from answer sets frameworks are far more general than cautious induction, as shown on the previous slide, they actually have the same worst case computational complexity as cautious induction. And each of the extensions that we gave do not increase this computational complexity. So I've talked about the learning frameworks, which I would say is what the systems can do and the problems that they can solve. I'm not going to go into too much detail on how the systems work, but I just wanted to give a little bit of information. So the ILASP systems, they're actually a family of algorithms ranging from ILASP 1 up to ILASP 4 that was released last year. They all solve exactly the same problems. So it's not the case that, say, ILASP 1 can only solve basic learning from answer sets problems. They can all solve the same learning tasks. The only difference is the scalability. So with each release, we've tried to push the scalability or the efficiency further. And they actually work very differently underneath in order to achieve that. ILASP 1, which has now been discontinued and is no longer being supported, had some major efficiency issues when it came to negative examples. So even if there was only one negative example in the learning task, it could actually take an extremely long time to solve a learning problem. ILASP 2 resolved this, but it had some scalability issues with respect to the number of examples. We then released an iterative approach, which was very similar to ILASP 2, called ILASP 2i, but because it was iterative on the examples, it was able to deal with much larger sets of examples. And then ILASP 3 and 4, which I'm going to say a little bit more about later on, extend this to large numbers of noisy examples. So now I just
Mark, sorry, somebody
Yeah.
is asking, is DP deterministic polynomial?
no, so well, I'm not sure what the DP actually stands for off the
No,
top of my head.
DP complete in the, it's
Yes,
I think it was slide 14,
So I'm
yeah,
not sure what
or
the DP
15.
stands for. I don't think it is deterministic polynomial, but it's essentially the combination of an NP problem with a co-NP problem. So you can split your decision problem into deciding one NP hard problem and one member of NP and one member of co-NP.
Yeah, great. And have you studied average case complexity?
No, I haven't. I would suspect
Okay.
that that's where you may get a difference between cautious induction and learning from answer sets.
Perfect. Yep.
But I
Thanks.
haven't studied it. Okay. So I want to say a bit more about learning in the presence of noise now. What I've presented so far has had quite a strict assumption that every example has been correctly labeled. So this means if you give a positive example, I'm only interested in hypotheses that have at least one answer set that extends that example. In real world tasks, it may not be the case that all examples have been perfectly labeled. So we may have said something's a positive example, but in fact it's a negative example. And so we may not want to be so strict about enforcing that all examples have to be covered. So for non-noisy cases, what we usually do is we search for a hypothesis that covers all of the examples. And then if we have to choose between two candidate hypotheses that cover all of the examples, we would pick the shorter hypothesis. If they're both the same length, then we just pick arbitrarily. By length, I usually mean the number of literals in the hypothesis, although the user can actually control this to some degree. In noisy tasks, we do it slightly differently. So we're still trying to minimize what we call a scoring function, but this scoring function now has two components. It's the length of the hypothesis plus the penalties of all of the examples that are not covered by that hypothesis. So effectively what this means is you can choose not to cover an example so long as you pay the penalty of that example. The penalties usually will be the same across all of the examples. So you usually give a fixed integer weight to every single example, but there are cases where you may want to give different weights to different examples. So for instance, you could model things like trust in the sources that the examples have come from and say that examples that have come from a particular source are highly trusted, in which case you give them a higher penalty for ignoring them. You could even say that some examples are definitely non-noisy and give them effectively an infinite penalty. Now, I said I didn't want to go into a lot of detail on how the systems work. This is a diagram from a paper we've got that's under review for TPLP at the moment, called Conflict-Driven Inductive Logic Programming. If people are interested, then the paper is already on arXiv, so you can go and find it. But I just want to talk a little bit about, at a high level, how the ILASP 3 and ILASP 4 algorithms work, because they're very different to how the previous ILASP systems worked. And this is to take into account noisy examples. So the basic idea is that it's an iterative approach. The first step is to search for a hypothesis that conforms to a set of what we call coverage constraints. Now, I'm going to say a bit more about these coverage constraints later. At the start of the algorithm, they will be empty. And so the first hypothesis that we find will usually be the empty hypothesis. We then proceed to the next step, the counterexample search, where we check whether the examples that we've been given are covered by the hypothesis. Now, if they all are, then we can return the hypothesis. Because it's obviously the optimal solution of the task. If not, and it's an example that we weren't expecting to be uncovered, then we can take this example as a counterexample. This counterexample then goes forward to the next step of the approach, which is called conflict analysis. This is where we try to work out why the hypothesis that we found doesn't cover the counterexample. Now, I could do a talk on how this actually works within ILASP, but I'm not going to, because I don't think many people would be all that interested in it. But basically, what we're trying to do is translate this counterexample into what we call a coverage constraint, which is effectively just a Boolean formula over the hypothesis space that says, for instance, you have to have at least one of these rules in the hypothesis in order to cover the example, or none of these rules, or some Boolean combination of those kinds of formulas.
So Mark, I guess that's similar to analysis within Klingo, right?
Yes.
The analysis step.
Yeah, so it's based on conflict-driven ASP solvers and conflict-driven SAT solvers. That's where the terminology comes from. There are a few differences where it's not exactly the same, but it's similar in that when you find that something is not an answer set or is not a model, you try to find an explanation of that conflict. And then you add that and you carry on solving. The one difference actually between what we do and what normal conflict-driven solvers do is that we don't just take this this coverage constraint that we found and carry on searching in the next step. There's actually something in between called constraint propagation. This is the bit that makes ILASP 3 and ILASP 4 much more efficient when it comes to noise. Because what we could do is just say, well, we don't cover example 1, say, if we ignore this coverage constraint. But if example 1 has a very low penalty, then the hypothesis search may choose to ignore example 1. And then we go round to the counterexample search, find a very similar example, example 2, and find exactly the same coverage constraint in the next iteration, and keep going and going and going and finding the same coverage constraint until the sum of all of those penalties has reached a high enough level for the hypothesis search to change direction. So what we do instead, to avoid that scenario, is we try to propagate the constraint. So this means that we search for all of the other examples that would not be covered if we chose to ignore this constraint. And then once we've done that, effectively, we're boosting the penalty of not covering that constraint. And usually it will lead to significantly fewer iterations of the whole algorithm. So it can make things much, much faster. So that's as technical as I want to get about the learning algorithms. As I said, I don't really want to go into a huge amount of detail. This is an experiment that we did to evaluate the ILASP 3 system. So this was the first of the conflict-driven approaches, where we were testing ILASP 3 on a noisy version of the Hamilton problem that I showed you before. So we randomly generated some graphs of up to size 4, half of which were Hamiltonian and half of which were not. And then rather than just giving correct labels for all of them, we picked a percentage of those examples and switched the label. So that's either 5, 10, or 20%. And that's shown by the red, green, and blue lines respectively in the graphs. And what you can see is that actually, if we give sufficient numbers of examples, so around 200 examples, they all seem to converge around the same point, getting around 95 to 97% accuracy on an unseen set of test graphs. But what's interesting is that as you have more noise, you need more examples in order to reach the same level of accuracy. The algorithm does take slightly longer if you have more noise, and that's because the more noise you have in a problem, the more iterations you're likely to need of the conflict-driven approach in order to converge on the optimal solution. That was a synthetic experiment just to test. I mean, the reason we do these synthetic experiments is to evaluate on a known quantity of noise. Obviously, we also want to do experiments on real data sets because they have a more realistic distribution of noise. And we wanted to compare, in this experiment I'm going to show you, we wanted specifically to compare ILASP to other algorithms that operate under the answer set semantics. Specifically, the reason for the comparison is that ILASP is guaranteed to find an optimal solution of the task, whereas some other approaches are not guaranteed to find optimal solutions, even though they do have a similar notion of scoring where they'll sort of push towards an optimal solution or a preferred solution in the sense that ILASP defines it, but they don't guarantee finding this optimal because they take some shortcuts along the way. And what we've actually shown is that by finding the optimal, the solution that ILASP returns on average tends to be more accurate on unseen data than the hypotheses that are found by current approximate algorithms. Now, I want to stress the word current in that sentence, in that I'm not saying that there are no approximate algorithms out there that could compete in terms of accuracy. In fact, we do want to, in the future, work on approximate versions of ILASP because it may be more efficient to do so. It's just that we've shown that on existing data sets, these existing algorithms that are approximate are not quite as good in terms of accuracy. So the first real world experiment I want to show you is one that has been used to evaluate the INSPIRE system for ILP. This is a Brave induction system, but this problem can be represented easily in Brave induction, and the task that we give to ILASP is effectively a Brave inductive task as well, because there are no negative examples. The real world task is to try to split a set of sentences that have been labeled by their various chunks. So tie opposition party to boycott general election should be split into tie opposition party, to boycott, and general election, according to the data set. And there are two different versions of this data set. There's one with 100 examples and one with 500 examples. And then there are various categories of sentences. So some of them have come from newspaper headlines, some of them have come from image captions. I'm not actually sure what students means in that, maybe student language is different. But then the interesting thing to do is to actually compare the relative performance of the systems on the instances of this data set with 100 examples and 500 examples. So in every single case, ILASP finds a hypothesis with a higher F1 score, and this is because of what I was saying before about finding the optimal solution. But what's more interesting is the fact that in 4 out of the 5 cases, if you compare the F1 score of ILASP to the F1 score on 500 examples, it's higher in 4 out of the 5 cases, whereas for INSPIRE, actually giving more examples, given 500 examples, the F1 score decreases. Okay, and this is actually because INSPIRE has a timeout that means if it hasn't, at one stage in its algorithm, if it hasn't found the best solution, so the best solution after half an hour, then it terminates and finds the best solution so far. And so this means when you give more examples, it means basically that it's less likely to have converged to the optimal solution. And so therefore it finds a lower quality hypothesis overall. At least that's what I think is going on. I haven't, I'm going off their results. I haven't actually replicated them. And so then the other interesting thing to point out is that where INSPIRE has a maximum computation time of half an hour for one part of their pipeline, you'll notice that actually every single ILASP computation is under half an hour. So although we're guaranteeing finding the optimal, which is a more difficult task, we are actually faster than INSPIRE on this data set. Okay, so this is the conclusion of part 1. I know I've only got about 15 minutes left, including time for questions if anybody's got any more questions. But the second part I can go through much quicker because it's only on more recent work. So these ILASP systems, I just want to finish by saying the framework that underlies them is very general in that we can learn any program up to strong equivalence, at least in theory. The systems themselves can learn even in the presence of high proportions of noisy examples, but where they fall down at the moment is scalability with respect to the size of the hypothesis space. So if you have a very large hypothesis space, because ILASP actually starts by generating this hypothesis space in full, it may be that although the algorithms are theoretically capable of finding the inductive solution or the optimal inductive solution, in practice, they may never terminate or they may run out of memory. And then finally, ILASP is available to download from ilasp.com. So please feel free to start using it and email me if you've got any questions on how to get started. But now I just want, well, actually, first of all, does anybody have any questions on that part before I move on to the second part? No? Okay. So now I want to talk about some more recent work.
Somebody is asking, which is a feasible size of hypothesis? In the chat, yeah.
Hypothesis or hypothesis space. So hypothesis, well, I mean, they both depend really on the structure of the task. Hypothesis, it's not really too much of a problem if you have quite a lot of rules. You tend in the iterative algorithms to have more iterations because in the early iterations you tend to find shorter hypotheses and you have to find quite a lot of weight almost to justify learning a very long solution. But in terms of so that might run for quite a while in terms of the iterations, but it's not the case that it won't terminate or run out of memory because of that. The hypothesis space, on the other hand, if that's too big, then you do run into memory issues, or it may never terminate because each step in the algorithm may take a very long time. Now, it really depends on the structure of the learning task. So if you have observational predicate learning, which means that the examples you've given are for the same predicate as the target predicate you're trying to learn, you have no recursion, you have no predicate invention, you have, say, no negative examples because they're actually computationally, they raise the computational complexity, then you can get away with hypothesis spaces that contain many thousands of rules. So sometimes even hundreds of thousands of rules, which means 2 to the power of that many solutions. But in practice, if you're pushing the computational complexity in terms of negative examples, and then you're including the possibility of, say, learning recursive definitions, then your hypothesis space likely won't, or the system won't be able to cope with hypothesis spaces with hundreds of thousands of rules, because the groundings of those programs will be very, very large in practice. But as I say, it really does depend on the structure of the learning task, so I can't give a concrete number. Okay, so now this second approach that I'm going to go over is aimed at dealing with that bottleneck with respect to the hypothesis space. So there's 2 aspects to this system. One is the increased scalability with respect to the hypothesis space, and the second is that it's able to incorporate a notion of domain-specific optimization criteria. So I'm going to go into more details on the optimization criteria now. What I mean by this is when we're trying to choose between 2 different hypotheses, what measure should we use to choose? So I introduced a scoring function before where we were balancing the length of the hypothesis against the penalties of examples that weren't covered. And that's the usual optimization criteria within ILASP. We may want to use other optimization criteria, and this optimization criteria may even be domain dependent. So just to give an example to motivate this, in some domains, false negatives are far more dangerous than false positives. So in event detection, it's usually more dangerous to miss an event that did occur than to erroneously flag an event that did not occur, because you can correct for the latter later on. Similarly, in medical diagnosis, and I mean, it depends on the disease, but usually it's more dangerous to misdiagnose somebody as not having a disease that they do have because you fail to treat them. Whereas if you erroneously say that they do have a disease that they don't have, then this can be picked up by a doctor later on with a second test or a different kind of test. So usually you'd want more false positives than false negatives. But I'm not a medical expert, so I may be wrong on that. In other domains, though, the reverse is true. So for instance, in access control, false positives are far more dangerous than false negatives, because if you grant somebody access to something that they shouldn't be able to see, you can't undo that. They've seen something that you didn't want them to see. Whereas a false negative, while it may be annoying in that the user can't see something they should be able to see, you can correct that later on. And so depending on the domain, we may want to change the mechanism of scoring within our learning approach. As I showed in the previous part of the presentation, there are a few ways of, or 2 ways that within ILASP of measuring the score of a hypothesis. For non-noisy tasks, we usually just do it as the length of the hypothesis. For noisy tasks, we combine this notion of length of the hypothesis with the penalties of examples that are not covered. But there are lots of other optimization criteria that exist. So for instance, the number of rules within the final program, the number of ground instances of those rules, the number of variables within the hypothesis, or even the number of answer sets of the learned program. A general scoring function would be able to take any of these optimization criteria. And for a general scoring function, we just say that it has to take a learning task and a hypothesis and return a real number. FastLAS, the system that I'm going to present now, can't quite achieve this level of scoring function. It instead has a restriction on this that we call a decomposable scoring function. We say that a scoring function is decomposable if you can evaluate the score of each rule independently, add them all up, and this gives you the score of the overall hypothesis. So for some of the optimization criteria that I've given on this slide, that's obviously possible. So for instance, the number of rules, you just count each rule as one, add those up, and that gives you the number of rules. The number of answer sets you couldn't represent in a decomposable way. We are trying to extend this in current work to support non-decomposable scoring functions, but that's not complete yet. So now I want to say a little bit about the difference between FastLAS and ILASP. So FastLAS is based on the same learning framework as ILASP in that it can take a background knowledge, a hypothesis space, which I haven't actually mentioned this, but it's usually characterized by what are called mode declarations, which means that you give effectively schema for where predicates can be used and how they can be used within the hypothesis. And then a set of positive and negative examples. And the notion of solution is defined as before. FastLAS, or at least FastLAS 1, has some major restrictions, which are, firstly, all programs have to have a single answer set. So this means that the notion of brave and cautious actually coincides. And this is why actually the implementation of FastLAS only supports positive examples, because there's no need for the negative examples when you only have programs with a single answer set. And no predicate in the head of a hypothesis rule can occur in the body of any rule in the hypothesis or in any rule in the rest of the task. Now, this is quite a restriction because it means that we can't do things like learning recursive definitions, doing predicate invention, or doing what I mentioned before, which is non-observational predicate learning. These restrictions are being lifted in current work. We have a paper under submission at the moment, actually, on this, but I'm not going to talk about these today. But basically what we did was we started with a very simple subset, so far less general subset of what ILASP can do, but tried to make it as scalable as possible. And now what we're slowly trying to do is lift these restrictions and get up to the same level of generality of ILASP while preserving the scalability that we've achieved. So how we do this in terms of the scalability is that instead of computing the hypothesis space in full at the start of the task, we actually do something very different, right? Because if we were to compute the hypothesis space at the start of the task, it could be too big, which means by the time we get to the solver is overwhelmed, or even we could run out of memory before we even hit the main solving part. So what we do instead is that we actually try to use the background knowledge and the examples in order to compute a small subset of the hypothesis space that contains at least one optimal solution. And so this means that then we can give this what we call an opt-sufficient subset of the hypothesis space to a solver, and it has exactly the same guarantees as it had before in terms of finding the optimal solution within that subset. And because that subset contains at least one optimal solution, that solution found by the solver is guaranteed to be optimal overall still. So it's the same guarantees, but because this subset is usually significantly smaller, FastLAS is much more scalable than ILASP. Now, because I'm running out of time, I'm going to skip over the details of how we compute this opt-sufficient subset and just focus on the evaluation. So on the sentence chunking dataset that I was showing before, FastLAS, you can see, is significantly faster than ILASP. We don't have an average running time for Inspire, but as I said, they had a timeout of half an hour that they were hitting at least some cases. So we know that the running time of the two systems, or both systems, is actually faster than Inspire. And for 500 examples, the same remains. So FastLAS is still significantly faster than ILASP 3. I've since producing this slide, actually, because this is taken a different presentation, I've run it on ILASP 4, which is slightly faster than ILASP3 on this problem, but nowhere near the time that FastLAS is able to achieve. And then the second data set I want to show you just very quickly is an event detection data set that's previously been used to evaluate the OLED system. So the task here is that we're trying to learn rules that correctly predict when two people start and end a meeting. So this will be in terms of how close they are, their orientation, how fast each person is walking, and that sort of thing. Now, OLED is significantly faster than both ILASP and FastLAS, but OLED, like Inspire, is not guaranteed to find the optimal solution overall, which explains the slight difference between OLED and ILASP in terms of the F1 score. Now, you might think that FastLAS's performance is not that much better than ILASP, but actually for this data set, we gave ILASP a very small subset of the hypothesis space so that it could run with what we thought were fairly intelligently chosen rules, around 3,000 rules, which still means 2 to the power of 3,000 possible solutions, because each rule can either be in or not in the hypothesis. FastLAS had over 2 to the power of 44 rules because we gave it the entire hypothesis space, which means 2 to the power of 44 possible solutions. Now, obviously, this is huge compared to the hypothesis space for ILASP, and it turns out that although we thought we'd been intelligent in picking the 3,000 rules for ILASP, we weren't that intelligent because FastLAS was able to find a much better quality solution within the larger hypothesis space than the one that ILASP was able to find in the chosen subset of the hypothesis space. And that's why you can see a much better F1 score for FastLAS than for ILASP3. Okay, so that's about everything I wanted to say. FastLAS, as I said, it's much more scalable than ILASP, and it does support this notion of domain-specific optimization criteria, but it has some major restrictions, and that's what we're working on at the moment, trying to lift both the kinds of programs that we can learn in terms of recursion and non-observational predicate learning and so on, but also we want to support non-decomposable scoring functions. Okay, thank you very much.